Good morning, my name is Leonardo, and I'm going to present a paper entitled Monte Carlo and Particle Swarm Methods Applied to the Design of Surface Plasma Resonance Sensors. This paper was written by myself and my advisor, Professor Eduardo Fontana. We are from the Federal University of Brazil, Pernambuco in Brazil. Here's the introduction. What are surface plasmons? Surface plasma are electromagnetic oscillations confined to the interface between a metal and a dielectric, and here are the field lines of the surface plasmons. It's a resonant phenomenon. SPR stands for surface plasma resonance, and being so, this effect is very sensitive to the variation of the optical constants of the two contact media, making it very suitable for optical sensing applications, such as the detection of biomolecular interactions, thin film characterization, and gas sensing systems. Although one cannot excite surface plasma by direct illumination of a planar metallic surface, they can be excited by using some prism coupling. There are main two types of configurations using prism. The first one is the Kretschmann configuration and the Otto configuration. The dielectric here in green is considered to be our sensing medium, and when its refractive index changes, the resonance curve shifts, and we can monitor the shift of the resonance curve looking in the variations of the reflectance or the incidence angle or the wavelength. In this work, we focus on the variation on the reflectance signal. So in order to design an SPR sensor, we need to optimize the parameters of the sensors to maximize the sensitivity of the sensor, which ultimately corresponds to maximize the quality factor of the resonance curve. In 2006, Fontana presented a systematic methodology to optimize those sensors using a direct search algorithm for Kretschmann configurations SPR sensors. He used as the decision variables the incidence angle and the thickness, film thickness, and tried to maximize the objective function, the sensitivity of the sensor, that equals to the rate of change of the reflectance in respect with the refractive index of the sensing medium. He used as the initial guess the critical coupling thickness. And the outcome of the algorithm is the optimum point that corresponds to a coupling coefficient equal to 2. So the challenge for design SPR sensors, I selected here 4. The first one is that the method described in the literature, they use a Lorentzian approximation as an initial approximation for the resonance curve. This approximation is very interesting because it gives us very good information about the physical phenomena and the sensitivity limits, but it does not describe exactly the resonance curve derived from the Fresnel equations. Those methods described in the literature, the majority of them, they only deal with Kretschmann configuration, in spite of the fact that the optimum coupling coefficient condition is in principle also valid for Otto configuration. The algorithm of the direct search, it needs a precise initial guess to avoid lack of convergence, and also deal with a non-trivial objective function. That's the sensitivity, and the reflect is the derivative of the reflectance in respect to the refractive index of the sensing medium. So in order to address those challenges, we have used 2 algorithms. Heuristic optimization algorithms, we select the Monte Carlo and the particle swarm optimization methods in the design of SPR sensors. The first one, the Monte Carlo, he generates a vast quantity of points randomly here in the search space, and evaluates the objective function in each point. Each point represents our decision variables, the parameters of the sensor that we want to optimize. So the Monte Carlo generates those numbers, evaluates the sensitivity in each point, and select the best point, that point that has the highest sensitivity. And this process can be repeated as many times as you want. The other method, the other algorithm that we have used was the particle swarm optimization, the PSO. In this algorithm, it tries to emulate the particle swarm behavior. It generates some particles here, and after these particles start to move with a variable velocity that depends on the global best of the whole particle swarm and also of the best of each particle individually. So it tries to, all particles goes near the best point that maximize the sensitivity of our sensor. So we have applied those algorithms to the design of SPR sensors. We implemented a Python-based web app that you can access using this link to the website, and try to design by yourself some SPR sensors with the sensitivity optimized. Here's the configuration of our problem. We define the search space. We first consider the two configurations, Kretschmann and Otto, using air as the sensing medium and gold for the thin film, the metallic film. And the constants of the materials were extracted from those references. So here in this table, we can see the results of the Monte Carlo and PSO compared with the direct search optimization algorithm. For the Monte Carlo and the PSO, we run the algorithms 3 times to check the consistency of the results. Looking for the Kretschmann configuration, you can see that the PSO has the best computational efficiency. It's 7.5 times faster than the direct search algorithm, and also is a kind of 27 times faster than the Monte Carlo algorithm. And here's the results for Otto configuration. You can see that for both configurations, the PSO results are the same in the 3 simulations. And the Monte Carlo has a slight difference between the results. And here we use less particles than the Monte Carlos. Here is our plot of the spectral dependence of the optimum sensitivity for different wavelengths. So for each wavelength, we run the PSO algorithm for the 2 configurations, Kretschmann and Otto, and for 2 sensing mediums, the air and the water. So you can see here this curve in the top. It describes the Kretschmann and Otto configuration for air sensing, and here's for water sensing. Both considerations present similar optimum sensitivity. One thing interesting here is that in 1.6 micrometer, we have sensors that has a sensitivity, optimum sensitivity, that is 2 times larger than sensitivity of SPR sensors in 1 micrometers. And this region is very interesting because it's the portion of the spectrum where low-loss optical communication systems works. So here also is the spectral dependence for the parameters of the sensors. Here's the optical thickness, film thickness, and here's the gap for the auto configuration. Here's the optimum incidence angle, the spectral dependence. And in particular, for the case of 1.6 micrometer, we show here the resonance plots for the Kretschmann and Otto configuration using air as sensing medium. And we also show here the sensitivity curve. And we can see that in Kretschmann configuration, the first one, The optimum incidence angle is located before the resonance angle, whereas in the Otto configuration, the optimum incidence angle is located after the resonance angle. And for this particular case of 1.6 micrometers, the Otto configuration presents a slightly better performance than Kretschmann configuration. So here's the conclusion of our work. First, we could optimize the SPR sensors using Monte Carlo and PSO, and these algorithms can be applied for both configurations of prismatic coupling, Kretschmann and Otto, and also can be applied for other types of coupling. The PSO algorithm presented a better performance than the Monte Carlo and then direct search algorithm. And a Python-based web app was developed and is freely accessible for all scientific community called SUSO, Surface Wave Sensor Optimizer. Thank you so much for your attention.